So we reduced our stability problem to V disturbance equation. Now we are going to look into that how we are going to proceed further with the waveform definition that we have. So we discussed the temporal stability and spatial stability, and the procedure are similar for both, but the eigenvalue problem that we get at the end is slightly different for the temporal and spatial. But the overall procedure for both type of stability analysis is very much same. So we will proceed here with the temporal stability, and this waveform that we expressed the V perturbation as over here, we will substitute that waveform into the V disturbance equation that we reduced earlier. So upon substitution of this disturbance form into the V disturbance equation, we can reduce that to in this form. There are a little bit more mathematical steps are involved. I guess that won't be a problem. If someone want to get more details, they can sit and try this some mathematical step, and they will eventually obtain this equation. So once we have this, for the simplicity rather than v hat, we will just denote it as a phi, and this is the expression that we get finally out of it. So this is basically the stability equation for incompressible boundary layer, which is also known as OrrSomerfeld equation. Very popular equation for the people dealing with the stability analysis for the incompressible flow, where they find something called Tolman-Schlichting waves, and this is very crucial equation to identify the Tolman-Schlichting wave. So we will further look into how we are going to solve this OrrSomerfeld. So we can further rewriting this equation, we just express it in slightly more simpler form, where we took this phi common, and all the derivative we are representing with the d. So t raised to the power 4 is the fourth derivative, t raised to the power 2 is the second derivative, like that. And we have here, which is c, which is basically the phase speed, and that is basically going to be an eigenvalue for this problem. And yeah, so d is basically the derivative, as I told you. So d raised to the power 4 is the fourth order derivative. And finally, this equation can be reduced into an eigenvalue problem, where a tilde is a matrix, big matrix, b tilde is a big matrix, c is eigenvalue that we are seeing over here, which is unknown, and phi is also unknown, which is eigenvector. So we have to solve this equation to get eigenvalue and eigenvector, where a tilde and b tilde comes from the details that we provide to the mean flow, from the mean flow, and this matrices also include the information of alpha term that we are specifying. So all the details are included in this A and B matrices. So now we are going to see that how we are going to reduce this OrrSomerfeld equation to eigenvalue problem that we are seeing over here. So simply we basically solve this. This is a OrrSomerfeld that we seen above, and we basically solve this OrrSomerfeld between the surface and the boundary layer edge. So on the surface, we set the boundary condition, where on the surface we set the boundary condition for the phi is 0, because on the surface phi is basically the perturbation, V perturbation. We just renamed it over here, V perturbation as a phi. So V hat is basically the amplitude of V perturbation, and that comes under the, that is what we are going to solve it for. So on the surface there is no perturbation. So on the surface perturbation is 0, and the gradient of perturbation is also 0. So when we write this, so we can divide this boundary layer profile in the wall normal direction, we can discretize it into smaller nodes that we can call j1, j2, j3, starting from the surface goes to n, which is a boundary layer edge. So on the surface we are setting the phi as a 0, so phi1 which is on the surface is 0, and we are taking the gradient on the surface is 0, so the phi2 is nothing but the phi1. On the boundary layer edge, we are since the boundary layer edge, at the boundary layer edge, it is much far away, it is a free stream, so there is no perturbation in the free stream, because the perturbation can sustain in a when there is a velocity is in the within the boundary layer. There are the different subregions where the perturbation can sustain, and in the free stream, this again the perturbation is considered 0. So the phi n, which is towards the boundary layer edge, where the free stream velocity is phi 0 and the gradient of perturbation is also 0. So we can express in this form. So this is particularly the boundary condition for this this equation. So we have the equation, we have the boundary condition, now we want to solve it. So for solving this OrrSomerfeld, which is the OS equation, which is written over here, to solve this we will use the finite difference scheme, and it can be further discretized wherever the derivative we have, like phi double prime is the second order derivative, phi 4 prime is the fourth order derivative, something like that. So what we can do is we can apply this over here. So phi double prime, we can apply the second order finite difference. We have here the fourth order derivative, and according to that we can apply the another finite difference scheme, and then we can write this OrrSomerfeld after applying the finite difference in this form. And then once we get in this form, we can arrange this set of equation in this form, where in different matrices. So this will basically showing the different terms in both side, in left hand side and right hand side. And one thing to notice here, don't confuse with this C and this C. This C over here which we are seeing, and this C hat is nothing but the matrix, but this C is basically our eigenvalue that we are going to solve for. I just name this in the alphabet so that we can arrange systematically in a matrix form. So arranging this particular equation, writing for all the nodes. So we wrote this equation particularly for one node, for the J, and J is something like in one node in wall normal direction. So this is written for J, and we get one set of equation. We will write the same equation for all the nodes, and then we can arrange in this matrix form. So here this is something we will get some sort of penta diagonal matrix, and in the left hand side, and a kind of tri-diagonal matrix in the right hand side. And here we have C, which is eigenvalue, and this phi is arranged as in a column that are the eigenvector. So here we have the same equation that we seen above, which is eigenvalue. So eigenvalue problem, where A tilde and B tilde hold the mean term, information about the wave number, which is alpha, and Reynolds number, and C, which is a complex eigenvalue, and that we are going to solve for. We will be getting as a real part and imaginary part, and the real part will give the phase speed, and imaginary part will give the growth or decay rate. So when Ci, which is the imaginary part, when it is positive, it indicate of unstable growing wave. When Ci, which is imaginary part, is negative, then it basically tells that the wave is stable and it is decaying. So we can think this entire thing in this way, that we have the linear stability toolbox, we feed in there the mean flow and the alpha, which is wave number, and Reynolds number, and then we get the Ci, which is a indicate of growth rate, whether it is growing or decaying. Depending on that, we quantify whether the wave is unstable or stable. And then we change the alpha, we change the Reynolds number, we get the different growth rate. And then we for one fixed alpha, we change the Reynolds number, we get the different Ci. So for the different Reynolds number, we get the different CI for a particular alpha, and we change again the alpha, then for the different alpha we get the different curve for the Reynolds number. So like that we get the different curve, and we can say that if this CI is, as we seen, it is positive, then it is unstable. When it is negative, it is stable. So individual curves are showing different alpha. So different alpha, so based on this you can say that this wave associated with this wave number is going to be unstable over this Reynolds number, over this range. Wave associated with alpha 0.03 is going to grow over here, and then it is going to decay. So this is basically showing schematic of how the growth rate look like when you with the Reynolds number with a different alpha. So this is all about the stability. Now I think it is a good time to get into the code and look into how this works.